Okay, so now the recording is on, everything is working. Kate, going back to the problem 1A that you were talking about, right? So if we read the problem real quick, right? There's a couple keywords that they had. So it says the ideal gas shown initially occupies a volume of 1 liter in a container, right? So we have our initial volume, 1 liter, okay, in a container in contact with a thermal bath maintained at a temperature of 300 Kelvin. So maintained is a really key word there, meaning that the temperature is kind of kept constant essentially at 300 Kelvin. It says the gas is allowed to expand by reducing its initial pressure of 2 atmospheres slowly, right, to allow the gas to maintain its temperature until it reaches a final pressure of 1 atmosphere. So we're seeing a change in pressure, right? We're going from 2 atmospheres to 1 atmosphere. So let me put this as 1A, right? We're seeing a change in pressure for sure from 2 atmospheres to 1 atmosphere. And then think about it too, like they said that the gas is allowed to expand anyway. So if a gas is allowed to expand, we can assume also that the volume is changing too. I think that's pretty safe to assume. But really, even if you wanted to ignore all of that stuff, right, the key word that's going on is that the thermal bath is being maintained here, kept constant at 300 Kelvin. And it says the pressure is decreased to allow the gas to maintain its temperature, right? So what we're seeing here is no change in temperature, right? Delta T is equal to 0. And if we think about what delta U was back in I don't know, maybe the first week or two, right? We were talking about how even if it's not delta U, like just U in general, right? So I'm gonna erase this real quick. So internal energy, I don't want to write the U, I kept writing the delta U, just U, right? That was equal to 3/2 N being the number of molecules, kBT. That was the total internal energy. Well, you can see here that the total internal energy is merely dependent on whatever temperature you have. And if you wrote a delta U, it'd be saying 3/2 NKB TF, your final temperature, minus 3/2 NKB TI, your initial temperature, right? Since we obviously don't see a change in temperature, delta U would be 0 for this point, right? Because it's an isothermal process, it's maintained at a specific temperature, right? And that's what U, the internal energy, is strictly dependent on, pretty much, right? Just because U is equal to Q plus W, right, doesn't mean that it's, I guess, dependent on the work that you do, for example, on the piston. Like I said, also, just from the context of the problem, it seems like they're changing pressure and changing volume at the same time, right? But they're keeping the temperature the same. So whenever you think about internal energy, the only thing that can change internal energy, or the only thing that internal energy is dependent on, is a change in temperature. So since the thermal bath is kept at 300 Kelvin, you don't see any change in U. Make sense? Oh, I think she left. Shoot. Well, did that make sense for the rest? For 1A? Mm-hmm. Well, here really the only thing that isn't changing is the temperature, right? It says the gas is allowed to expand, so we can probably assume that there's a change in the volume there. And they already told us that the pressure changed as well, right? And we know that pressure and volume are inversely related to each other. So let's say if we have the pressure like they did from 2 atmospheres to 1 atmosphere, we cut it in half. We can also safely assume, for example, that the volume would be doubled. And that's what they're kind of saying, is that the gas is allowed to expand, right? But what's not changing is the thermal bath temperature. That's 300 Kelvin. And when you think about what internal energy U, or delta U, is dependent on, it's strictly dependent on, by its formula, it's only dependent on temperature. And since we're keeping the temperature the same, That's why U is, delta U is 0. Does that make sense? Okay, awesome. You sure? I can repeat it again. Yeah, exactly, right? Because, like I said, U is dependent on... Wait, hold up. Can you guys see my screen? Okay, awesome. Yeah, so U, the internal energy, is dependent only on a specific change in temperature, right? You don't see V and you don't see P for pressure, right, and volume in the equation. So it's only dependent on temperature. And you can also kind of, I guess, extrapolate certain ideas from the question itself, because they said pressure went from 2 atmospheres to 1 atmosphere, so it was cut in half. And they also said the gas expanded. If the gas expands, we can assume that also means the volume of the piston is expanding, right? And so we know that pressure and volume are inversely related. If you cut the pressure in half, we can safely say the volume is doubling. And so the pressure volume changes effectively cancel each other out, like you said, right? That's what you mentioned earlier. But what we noticed that isn't changing in the problem, they said that the temperature is being maintained at 300 Kelvin, right? That's the key word, that the temperature is being maintained. And if we're strictly looking at what U is defined as, 3/2 NKBT, that's the total internal energy. If the temperature of the bath isn't changing, then the delta U would be 0, because in that case, the internal energy is not changing at all. Does that make sense? Awesome. Wait, can you say that again? My bad. Yes. Yep, since delta H is equal to delta U plus P delta V, well, if we're not seeing any change in internal energy, this is 0, right? Then you'd be witnessing the change in enthalpy as being strictly related to P delta V. Well, right, that's an excellent question. Because if we look at, for example, like what part 2 is asking from us, right? It says determine the change in enthalpy. Let me write 1b. I didn't mean part 2, I meant part B, my bad. If they're asking for the change in delta H, right, the enthalpy of the gas during the process, then we're looking at strictly the change in P delta V at this point, right? And since you see the pressure being halved and then the gas is being allowed to expand, so that you can say then obviously, well, if the gas is expanding, causing that change in pressure, then the change in pressure will cancel out the change in volume because they're inversely related, right? But essentially what you're seeing here, right, for delta H, it'd be kind of like writing it this way. HF minus HI, where you have a final enthalpy and initial enthalpy, right? And if we're going by P delta V, right, you have some final pressure, some final volume, minus some initial pressure times initial volume, right? So PF VF minus PI VI, right? That's what you're looking at for your enthalpy there. Well, in that case, you obviously have your pressure isn't constant in this case, right? Because we already said that it's going to halve from 2 atmospheres to 1 atmosphere, right? So this is 2, this is 1, right? We have a VF and a VI here, right? And they already said that the gas is expanding. Well, if we're going once again by the ideal gas law, that whatever change you see in pressure, you see kind of an opposite change in volume. So if we halved the pressure, we should see a doubling in the volume, right? So let's say if the initial volume, like they said, was 1 liter, right? 2 times 1 liter. If the pressure was halved from 2 atmospheres to 1 atmosphere, then we should see the inverse change, right, in the volume. So instead of seeing the volume being halved as well, the volume would double. So then you see 1 times 2. Well, 2 minus 2 would give you 0 at that point, right? So you see there, like, that's kind of what's going on, and that's why it kind of confirms our answer for part A as well, just based on the ideal gas law. Because if that gas is expanding, right, just the definition or like the word expanding means that the volume is changing. They also told us, right, directly, well, okay, the volume is changing, awesome, sweet. You can change the volume, but keep the pressure the same. Like you can have like a machine that kind of keeps the pressure the same inside a piston if you wanted to. But in this case, they're telling us that not only is the gas expanding alone, that the volume is expanding, right? But there's also that natural decrease in pressure that we would see with an increase in volume, right? So the volume increases, then we see a decrease in pressure. If we see a decrease in volume, we see an increase in pressure. That's because of the ideal gas law, PV equals nRT, right? Or PV equals NKBT, right? In which case, if you divide the V over, like I said, you can see that they're inversely related, right? So if I increase the V here at the bottom in the denominator, I decrease the value of my pressure. If I were to decrease the volume, the denominator, it increases my pressure, right? So there's an inverse relationship obviously going on here. So because the gas is allowed to expand, right, we know that there's an increase in the volume, right, just by the word expansion, right? So expansion means increase in volume, right? And then they told us essentially what we saw happen to the pressure. They said the pressure was doubled, or pressure was halved, my bad, from 2 atmospheres to 1 atmosphere, right? So if the pressure is multiplied by 1/2, then we can safely assume that the volume was doubled. And so based on our answer from part A, the fact that it's an isothermal process, right? So we should see no change in the internal energy, 0. Then that equation, delta H is equal to delta U plus P delta V, delta U becomes 0. So your enthalpy is strictly determined by change in pressure and change in volume. And if you were to write delta H as HF minus HI, you have your PF VF minus PI VI, your final pressure times your final volume minus your initial pressure times your initial volume, right? We saw the pressure was halved from 2 to 1, and based on the ideal gas law, we can assume that the volume was doubled, right? The inverse of that. And so what you end up getting is that your delta H, change in enthalpy, becomes 0 as well. Does that kind of make sense, like in the grand scheme of things, how we broke up the problem into pieces, like looking at the keywords in the problem as well to kind of figure things out? And yes, we said A was 0 for them. Yeah, essentially, yeah. We can safely assume that, yep. At least I hope. I mean, that's what made sense to me. Mm-hmm. Yeah, if you wanna go ahead and write, if you wanna hop on that free-form app real quick, and you wanna go ahead and show us kind of what you had written down for C, that'd be great if you can hop on that real quick. Okay, that's fine then. No worries. Yeah, we can probably try and figure that out later. But let's see here. So you said, can you repeat what you said about the multiplicity thing again, real quick? So that'd be your volumetric multiplicity. That would be V container over V molecule raised to the power of n, right? So if we think about, if we look at what C is asking, right, they want you to look at delta S energy, delta S volume, right? So the energetic entropy, the volumetric entropy, and then, yeah, that's it, I guess. Yeah, energetic entropy and volumetric entropy. So the components of that, right, for your, for your energetic entropy, right, we're looking at an equation KB ln of your energetic multiplicity, and for your volumetric entropy, we're looking at KB ln of your volumetric multiplicity. And like you said, energetic multiplicity, well, actually you said the volumetric multiplicity first, right? So that's your V container over V molecule raised to the power of n, and then this is the total degrees of freedom, so that'd be the number of molecules times the degrees of freedom per molecule, raised to the power of Q energy blocks per molecule times the number of molecules, basically, right? So that's kind of the general format that you're using for C. Now, let me look real quick. So determine changes, delta S energy, delta S volume, and the energetic, volumetric, and total entropy, respectively, of the gas. So they also want you to figure out total entropy, which would be a sum of both, right? Let's see here. So here's a quick question now, right? If we're looking at something like the energetic entropy, what is that dependent on, right? Because we have KB, that's a constant. We have the natural log of the energetic multiplicity. What do you think really affects energetic multiplicity here, right? Based on this system, you can see what we're changing in the system, what we're keeping constant, right? What does, say that again? So part of it, yeah, so part of it is the heat, the energy blocks, right? And obviously your degrees of freedom. But those are kind of constant for the system, right? That's generally constant for the system. Now, what else is it dependent on too? Because we have like degrees of freedom per molecule, right? And energy blocks per molecule. So what else is it dependent on? Oh, I'm just talking about the energetic multiplicity for now, like this part right here, like this part. But yeah, the volume also factors in for entropy. But if we're just looking at these two equations here, right, we're looking at KB ln of the energetic multiplicity, and we know that the energetic multiplicity is this format. So effectively, if this is constant, right, then really the only thing that entropy, the energetic entropy is dependent on is these two parts here, right? Well, we're assuming, degrees of freedom, you have that's constant. You really can't change that for a gas, right? Or for or you can't change the energy blocks either. So how could we change the entropy, right? So a gas inherently will have a certain amount of degrees of freedom, a certain amount of energy blocks, right? That's kind of built into the identity of a gas. So how could we increase the entropy or decrease it then? What factor could we physically, like ourselves, could we change? Exactly, excellent. So the number of particles is it's something that we can actually directly change, right? For the energetic entropy. Now, do you see any change or any indication of any change in the particles for that problem? So, I mean, I won't say anything else, but does that make sense? So if you're looking for delta S energy, right, the one thing that we can actually change, right, because we can't change the identity of a particle. We can't change can't change what a particle is or who a particle is, right? But we can change essentially how much of that particle there is, right? And so that can effectively change our, energetic entropy. So there you go. Now, yeah, go ahead, Matthew. Yes. Yep. Oops. Hold up. Sorry about that. Oh, what went on there? Okay. Can you guys see the screen better again? I don't know why it like minimized there real quick. Oh, I see something in the chat here. So would we use the 2 for both the initial and the final? I know they cancel out eventually, but I'm just asking for the fraction. That makes sense. So that's, you're asking about the volumetric entropy? Gotcha. So yeah, let's get to that here. So they're asking us about volumetric entropy, right? Let me move this over here. Then yes, since essentially what we're looking at here based on the context of the problem is that if they halved the pressure, like I said, we can safely assume that they doubled the volume as well, right? That's how the pressure and volume are related. They're inverse relationships, right? So that's what's going on there, right? They didn't really say it, but we can infer it. If they said the gas is expanding, right? The gas is expanding. Like I said, so if expansion means an increase in volume. And then they specifically told us what was the result of that increase in volume. It ended up having the pressure. So if it halved the pressure, that should mean it has that inverse effect of doubling the volume. And if the volume was 1 liter, then the expected new volume, the final volume, would be 2 liters. And so if you're basing things on this second equation here, right, for the volumetric entropy, then effectively your V container F would be 2 liters, V container I would be 1 liter, right? And I'm guessing you guys probably know how to kind of manipulate that around for a change in the volumetric entropy. You'd have delta SF minus delta S is SF minus SI, and then you just plug in your volumetric multiplicities and stuff. You end up with this kind of general final format where it's VF over VI, right? Because the volume of the molecule is constant. That won't change, right? That's kind of the ending format that you got. So that's kind of what's going on there. Now, let me see here. I think, so they want you specifically then to figure out a value for, what's it called? For the volumetric entropy, right? And so, let's see here. You have KB. You have your final and your initial volume, right? We can kind of get those. Like I said, we can infer those. That's not a problem. Now, the only thing that's kind of left is looking at number of molecules. They never really told us the number of molecules or the number of particles there are, right? Any ideas as to how we can figure that out? And let me see here. I know Thomas is on the free form. Thomas, I'm relying on you, son. Do you want to give it a shot? Let's kind of talk this through. So if we want to figure out number of molecules, right? And think about all the different pieces of information that we already have existing. All right, we know the temperature. Well, excellent. There we go. Someone got it. PV equals nRT, right? That's one form of the ideal gas law that we could use, right? But once again, I think it would probably be preferable in this course to use the second form, which is PV equals NKBT. That way you can have the number of particles instead of the number of moles, right? I think that's probably easier to do. I was saying, like, you're the only one on the freeform whiteboard, so I was wondering if you wanted to like show us how we can get the number of molecules there. But effectively, yes, you would use that ideal gas law equation, PV equals NKBT. You plug in all the pressure, volume values that we talked about before. You plug in your temperature that we had from the problem, part A, right? And then that's how you can get your number of molecules, plug that into your volumetric entropy, right? And then you're solid. And remember, they want you to figure out the total entropy, and total entropy is the sum of both of these together, right? So total equals Sn plus Svol, right? Your energetic entropy plus your volumetric entropy. And that's how you can get your total. And remember, we said that the energetic entropy is dependent on the number of molecules that we put in. And there's no indication that those changed. We didn't increase the number of molecules or anything like that. So, yeah, I mean, we already kind of talked about what delta S energetic would be. And so simply you would just, your total entropy will just be that sum right there. So we're saying delta S energy is 0 because, okay, is equal to 0. Well, N is not 0, right? We have molecules N there, right? That's N is the number of particles and the number of molecules. What I was saying is that your energetic entropy is based on your energetic multiplicity. And that's also based on degrees of freedom, energy blocks, and the number of particles, right? Degrees of freedom and the energy blocks are strictly pretty much dependent on the identity of the gas, right? What kind of gas is it, right? So you can't change who the gas is. You can't change what the gas is. But what you can change, like what we can physically change, is the number of molecules. There's no indication that the number of molecules changed, right? So final number of molecules, initial number of molecules hasn't changed. Degrees of freedom and energy blocks haven't changed either because we're not changing the identity of the gas. So effectively, yes, delta S energy is 0, right? But at that point, now we're trying to figure out the volumetric entropy, and we know that the total entropy is the sum of both. And so now it's just a matter of calculating your volumetric entropy, adding it to your energetic. Sound good? Okay. Makes sense for everybody else as well? I hope you're feeling better. Let's see here. So any other questions about that part C right there for 1? Yeah, I would prefer to use the... No, you're good. Yeah, I prefer to use the NKBT. You can still use the NRT if you want to. It's just that you'll get moles, and then you'll have to convert from moles to molecules using Avogadro's number. That's an extra step you don't want to have to do. But yeah, once you got the number of particles, right, using that, we're essentially going to use the pressure that they gave us in the first part of the problem, right, or the context of the problem initially, and then use, what's it called? What was I going to say? Shoot. Well, hold up. Let me look at this again real quick. The steps are right. I'm just like making sure like I didn't miss anything. Let's see here. So PV equals NKBT. Awesome. Yeah, okay. Yeah, okay, so that's not too bad. So I for a second there, I thought we had to calculate, like, factor in both pressures and both volumes, but I was just being stupid. The idea is for PV equals NKBT, obviously, like, PV over T, regardless of the combinations of P and V, and the temperature, obviously, PV divided by T is going to give you that NKB, right? So PV over T equals NKB, right? And you can divide over the KB if you wanted to as well, it doesn't matter. But the idea here is that either, it doesn't matter if you use the initial volume and the initial pressure or the final volume and the final pressure, it doesn't matter which one you're going to use, they have to both kind of result in that same constant number of molecules, because that's not changing, right? And that also makes sense anyway, because if we, like I said, if we halved the pressure and doubled the volume, well, half times 2, right? Half pressure times 2 volume, right? You're going to end up with PV again, right? So whether you use the initial volume and the initial pressure or the final volume and the final pressure, it doesn't matter. I just want to clear that up as well. Just make sure that your units are in pascals for pressure and your volume is in meters cubed, right? So the volume is in liters. We want to make sure that it's in meters cubed for this, to match up with everything else, right? So convert your pressure to pascals and your volume to meters cubed to make sure that everything kind of checks out. But yeah, you just use the pressure and the volume for where we had information from the initial part of the problem, divide that by the temperature, and you got your NKB, figure out what your number of particles are, and then use that for your volumetric entropy calculations. Does that sound good? All right. Yeah, for sure. Any other questions about 1C? I think that's probably a solid amount of information right there for that. Well, there we go. Yeah. I'm really trying my best. Yeah. So that sounds good. Anyway, so I think that's solid for 1C, right? Do you guys need help with 1D as well? I think 1D is pretty, like, straightforward. It says determine the changes delta F and delta G in Helmholtz and Gibbs free energy. So you're just using your equations for either of those, plugging in the necessary values and stuff, and then you're solid, right? Delta F, for 1D, well, I mean, I don't want to, because that would just be setting up the equation, setting up the problem anyway, but if you just get your equation for Helmholtz energy, get your equation for Gibbs free energy, right, then you can see all the values that you need to plug in. So Helmholtz energy, for example, is delta F equals delta U minus T delta S. What did we say delta U was? Exactly, right? So there's a value for delta U. Your temperature is constant. We had that 300 Kelvin. And delta S is whatever you determine for 1C. Calculate that. Boom, you got your delta F, right? Make sure it's in joules, right? Same thing for delta G. Same kind of deal. You have your delta H minus T delta S, right? If you do that, you're good. Just use the same values that you've been using for the previous parts. So I'll just write 1D use equations for, oh, someone's writing. I don't know if that was, oh, okay, I can see you here on the board. Okay, awesome. Go ahead for, like, if you guys have a question here, like whoever was typing, feel free to continue typing and ask whatever questions you guys have. Like while I'm asking something, if you want to type it on the board, that's totally fine. But yeah, use equations for Helmholtz. That's what I want to say. Helmholtz and Gibbo. Gibbs free energy. And use your previous values. So I think that's pretty solid. And let me scroll down here and look at some other things real quick. Oh, by the way, like, just discussing that YouTube stuff. So did you guys know that, I did not know this, but there's like a transcript for my videos, like sort of like captions or like subtitles, right? I didn't know that at all. I know there's a way you can enable like AI subtitles, like if you're using Google Chrome, and I can show you guys how to do that here if you don't know already how to do that. I use that a lot because if I can't hear the person, if I'm not really understanding them, then I can just pretty much have Google Chrome like figure out what they're saying for me. But yeah, apparently YouTube does that integrated now, and I can show you guys that as well. My writing looks messed up. That's weird. Oh, not on the stream, but on your end. Oh, that's interesting. I mean, I can try it. Hold up. Let me like maybe try and actually put more time into writing and making my handwriting look neat. Maybe that'll help. And Gibbs. Use your calculated values for each. Does that look better? Sweet. I don't know. I guess it depends, internet connection and whatnot, but at least we have some sort of like way to kind of collaborate and whatever. But yeah, I guess that's 1D. I don't know. Do you guys want to? Oh, I thought it was 3 problems, but problem 2 is massive. Yeah, where do you guys want to get started on problem 2? I mean, I guess it is tough to like just jump at a specific part, but yeah, the graph stuff is weird, and some of it isn't entirely making sense to me when I looked at it. Just because like I think like for one of the parts, I think part, what was it? D part 2, where they were saying show detailed calculation, how can you spot from the graph the fraction at which the system reaches equilibrium, right? Now, correct me if I'm wrong, because like I said, I haven't had a chance to fully look at like all the background and theory behind all this stuff again, just to refresh my memory. But delta G equaling 0 should be that should be when a process reaches equilibrium. But the way that they're defining it, I believe, is that they want it to be when delta Z is at a minimum. That's when it reaches equilibrium. That's what I kind of understood from that. So let me go ahead and write this off to the side here too. I mean, I guess we can work through it anyway, like we did, and I didn't give too much away. I don't think so. I think this is a solid way of going through things. So, all right, let's just go through it. So we have glucose isomers. It says glucose can exist in many isomeric forms. In solution, okay. Two of the most abundant isomers of glucose are alpha D-glucose and beta D-glucose. Okay. How do you consider the anomeric conversion of glucose in solution? Okay, starting with freshly dissolved. Alpha is the reactant, beta is the product. Proceed spontaneously until equilibrium is reached. Multiplicities of both are similar, with beta D having a slightly bigger number of microstates than alpha D by a factor of 28/25. So basically, alpha D is 28/25 times bigger than beta D. I guess that's what they're saying there for that part of the problem. And they want us, for part A, to determine the difference, right? The change in entropy, essentially. Well, yeah, sort of, yeah, the change in entropy between beta D and alpha D, right? In joules per mole Kelvin. So that's more or less just figuring out a delta S value, right? Where it's like SB minus SA, right? And you'd use your same, format that you have for delta S, or for S entropy, right? Going on, like for volumetric entropy and energetic entropy, we already said those values are like N, KB, Ln, and then your multiplicities, right? Now, I guess, what was I going to say? You also kind of factor in the idea that the multiplicity of, A is equal to 28/25 of B. Is that what they said? Hold up, let me read that again. B has, okay, no, I got that the other way around, I believe. So B is 28/25 times as big as A, right? And so this is pretty much the key to solving this, I think. Essentially, you would just use, like how we've always done so far, figure out the change in entropy. You know how to set up entropy problems. You know how to set up the entropy equation. You have your multiplicity for B, right? You have your multiplicity for B, and you have your multiplicity for A, right? And if you use this kind of like the last part in that sentence right there, where that A is bigger than B by a factor of 28/25, then that's how you can go ahead and figure out your change in entropy, essentially, right? Let's see here. Is there anything else they would want you to kind of look at just by looking at this stuff? So, all right, NKBLN, all right. So one last thing, I think. Can anybody tell me what N is going to be? What are a number of particles here? Excellent. So why is that? I guess that's a fair argument there. When in doubt, use Avogadros. But excellent. 1 mole, right? What do you see in the problem? What are they even asking you about? They're saying, let's read that more carefully. Determine the difference, S beta D minus S alpha D, right? In entropy in joules per mole Kelvin, right? Normally, when we're looking at things, right, your entropy is just going to be in values of joules per Kelvin, right? And whatever number of molecules we plug in, that's however many molecules we plug in. But since they're specifically looking at and they're asking for joules per mole Kelvin, that's why we use Avogadro's number of molecules there. So that's the number of molecules, the number of particles that we're looking at is Avogadro's number, 6.022 times 10 to the 23rd. That's our N, because in the units, they're telling us that basically we're looking for our N to be in just 1 mole, and that 1 mole is just Avogadro's number of molecules, right? But maybe, I don't think that would be, you could also see like, yeah, so someone said if you have one glucose to another glucose, just by looking at the reaction expression that they have going on there, they only have 1 mole and 1 mole of each like substance on either side. Sure, I guess we could go by that, but I think it's far safer and far like more direct, and you can kind of see that they're asking you about Avogadro's number of molecules because that's the units that they're looking for. They're looking for joules per mole Kelvin, and 1 mole of glucose is Avogadro's number of molecules of glucose, right? But that's what's kind of going on there, and that's what you got to keep an eye out for. Another thing, just for natural log properties, right? So I went over this in my last content review. I made a PowerPoint for the readings. That's on the Google Drive. It's in the announcements section for 132. And it's in the resources section as well. Now, N, depending, well, it's not really depending on, like, I mean, let's say, okay, so let's say you know that your S is equal to N KB ln and then some multiplicity, right? Or actually, let's say it's just KB ln of your multiplicity, right? That's what it should be. Now, if we were doing something like energetic entropy, right? If we're doing something like energetic entropy, then we might have like KB ln, say NF, right? Where F, your degrees of freedom, is the degrees of freedom per molecule. N is the total number of molecules, and then that's raised to the power of number of molecules times energy blocks per molecule, right? So for natural log properties, right, if you have an exponent like this inside the natural log, you can essentially just pull it out to rewrite it as NQ ln, and then you leave the base alone, right? Now, this N, like we said, is the number of molecules. If the number of molecules that we're dealing with just so happens to be Avogadro's number, Na, number of molecules, right? NaKB, based on some rearrangements on the ideal gas law, and that's something that I went over in the week 2 PowerPoints, I believe. Those are also uploaded on Google Drive, and there's a video on YouTube that I uploaded as well explaining that. But essentially, and this is a really good rule to remember for rearranging these things, and it can help you avoid an overflow error if that's really common for you. But NaKB can be rewritten as R, because effectively the Boltzmann's constant is simply your ideal gas constant divided by your Avogadro's number, right? So Na times Kb can be rewritten as R. So instead of saying 6.022 times 10 to the 23rd molecules, right, times 1.38 times 10 to the negative 31 joules per Kelvin, whatever, right, you can simply just write, if you have NaKb like that, if you see that, make that an R. Then you just have 8.314. Much easier for the calculator to do, much easier for you to input, far less mistakes, right? So that's not too bad. So that's what I recommend going for when you're solving those types of problems. And then another thing too is if, for example, they gave you a certain amount of moles, let's say they said 3 moles, right? Then when you're plugging in something like the energetic multiplicity where you have number of molecules, and you have 3 moles, let me quick question, right? How would you calculate from moles to molecules? What would you do? Yep, exactly. Multiplied by Avogadro's number. So 1 mole is Avogadro's number of molecules, right? Well, you could actually calculate what this is, right? It'll be a big number. Instead of plugging that big number in here, right? So you'd have essentially what you would write it as like 3NaQ in that case, right? Instead of doing that, instead of writing that big number out, this would essentially be like 18 times 10 to the 23rd, right? Roughly. Now, instead of writing 18 times 10 to the 23rd times the number of energy blocks per molecule, whatever, right? If you just keep it as 3Na, and then pull that 3NaQ on the outside, then this NaKB becomes R once again, like I said, right? And then that just makes things a lot more easier. Does that make sense? Yes, no, maybe so. Well, that's just because when you're doing that rule, you pull out the entire exponent anyway, right? Um, and the Q remains the same, right? Just that's because the identity of the ideal of the gas, right? But the NaKB, that becomes R. So effectively, you'd have like 3RQ ln and then whatever the base is left. Does that make sense? Yeah, I mean, yeah, like I said, you would pull out the Q too. It's just that the rule requires you to pull out the entire exponent. Yeah, go ahead. Oh, I was just making up an example. Like I was saying, like if you had a certain number of moles, right? Instead of writing out the actual number of particles, you can just leave it as 3Na, pull out the 3Na, and then your NaKB becomes R. And that can help prevent an overflow error. Yep. Mm-hmm. No problem. Um, like I said, that's kind of the gist of what's going on for 2A is that you find that change in entropy, right? And then your number of molecules just so happens to be Avogadro's number of molecules because we're dealing with joules per mole Kelvin. That's specifically what they were asking for, right? But how about looking at 2B now? Let's see here. It says 2 forms of glucose have different enthalpy. In fact, formation of the beta D form is slightly exothermic as some energy is released as the bonds rearrange. So we have a difference in the delta G from A to B of negative 1.43 kilojoules per mole. So now they just want you to figure out what delta H is, basically, right? They gave you temperature, 25 degrees Celsius, right? They gave your delta G value. And let's see here, what else do you have? And from part A, you would essentially have your delta S, right? So anyone want to, I guess let's see here, whoever, yeah, I guess, well, Thomas is, yeah, Thomas or Caitlin, if you guys want to write out what you think would be kind of the setup for that, feel free to do so. Oh, you didn't do it yet? Okay. No worries. Do you want to kind of maybe suggest at least verbally what's going on here, or you guys like are just kind of a little bit lost right now? Mm-hmm. Yep. So in that case, we would have a negative value, right? We should expect a negative value for delta H. Absolutely. Um, Now they're looking for delta H. They gave us delta G. They gave us a temperature, and we have the entropy from before, right? So what do you think we could do to figure out delta H? Yeah, hold up. Let me zoom out. Let's see here. I don't know if you, yeah, you might be writing over here. So try and like, I guess navigate to 2B somewhere. No worries, yeah. I mean, I hope it works out properly, but if it doesn't, like we can probably just stop using it, honestly. But I just figured we'd try it out. Okay. Okay, I see it. Awesome. Let me zoom in. So that's one equation, right, for delta H, but we don't necessarily have information, for example, about pressure or volume, right? So do you know of another equation we could use that involves delta H that could factor in some of the other units that we have, like temperature and all of that? Because remember, we have Gibbs free energy. Excellent. Yep, exactly. And so they gave you what delta G was from A to B, right? They said that was negative 1.43. You're finding their delta H, that's what you want to figure out. And then you have your temperature, that's 25 degrees Celsius. We can convert that to Kelvin by adding 273, right? Um, and then you just use your delta S from 2A, right? So if you just rearrange that equation, you should be able to get your delta H. No. So since the reaction is moving forward, right? If it's a forward reaction, then what do we call it, right? If that reaction tends to move forward in the direction it's kind of supposed to, spontaneous, right? So let me write that down real quick. So delta S positive means spontaneous. Delta S negative means non-spontaneous, right? And then for delta G, positive means non-spontaneous, and delta G negative means spontaneous. So if they told us that the process here was had a delta G of negative 1.43 kilojoules per mole, then that's a spontaneous reaction. And then that should also help confirm that our answer should be, that's kind of like a sanity check right there. Because if they told us that the delta G is negative, then we should have expected to see from 2A that our delta S should be positive. But yeah, does that make sense? Awesome. So that's kind of the gist for 2B, what you're doing there. Use that Gibbs free energy. Now we look at 2C, right? Analyzing the possibility of equilibrium in the process stated above if 100% of alpha D glucose turns into beta D glucose with that same delta G. Okay, well, they're asking, first of all, the change in Gibbs free energy if during the conversion only 1/4 of the glucose ends up as beta D and 3/4 ends up as beta D. So let me do like a 2C1 kind of deal here. It says, what would the change in Gibbs free energy be if only 1/4 of the glucose ends up as beta D And then they also asked if 3/4 becomes beta d, right? Well, let's see here. If we want to think about the delta G as some final state and some initial state, right? That's generally how we think about things. Some final state, free energy, and some initial state free energy. Instead of looking at like G beta minus G alpha like they have there, right? This would be a better way of thinking final and initial, because here's the thing. Not every reaction will fully go to completion like that, right? You won't go from 100% alpha to 100% beta, right? You might have a mix of both in your final state, right? So what they're asking you is, okay, well, what if in that final state we only had 1/4 end up as beta, right? Then that would mean how much ended up as alpha. So if 1/4 beta, then, yep, exactly, 3/4 ended up as alpha, right? If 3/4 ended up as beta, then 1/4 ended up as alpha, right? That's the second question that they were asking about, right? Now, once again, we kind of think about a final and an initial state, right? So, your final state would be made up of what? If we're saying that, going by that idea that not every reaction kind of goes to completion, and they're telling us clearly here that it isn't going to completion, and then that we should have kind of a mix going on, right? So we should have in our final state some beta glucose, and obviously, like as we said, if you have 1/4 of the glucose as beta, then 3/4 should be alpha. So what should we say for our final state? It should be what? If we were to write an equation for the final state, like GF, if we said GF is equal to something. Well, that's just delta G in general, right? They said delta G was GB minus GA. I'm saying just for your final state, if you were to look at that final state, if we wanted to like look at what it's made up of, we said it was 1/4 beta and 3/4 alpha, right? So remember they said delta G was written as GB minus GA. I prefer to write it as GF minus GI firstly, just to kind of get an understanding of what's going on final state and what's going on initial state, right? If we were to rewrite this as GF minus GI, your final state should be made up of what? Like, should it be made up of beta only, alpha only? How can we write GF? Should I say A plus B, A minus B, half of A plus half B? Like, what's going on here? So we're getting closer, right? So we have that final state has a mixture of alpha and beta. So 1/4 of it has to be beta. And we said that 3/4 has to be alpha. So you can kind of rewrite it as 1/4 beta, and you have 3/4 alpha. That's kind of like your mixture for your final state, right? Or we could kind of also say it just to kind of look at the, make it in the same terms as everything else. We can say 1/4 GB plus 3/4 GA. right? We can kind of say that that's what's going on for our final state. How about our initial state? That one should be pretty simple, right? If we started off with alpha glucose, then well, that would be for the second question, right? This 3/4 and 1/4, right? But if we're just looking for this first condition right here, if we're looking for that first condition, our final should be a mixture of 1/4 beta, 3/4 alpha. But what did we start off with, right? We're trying to convert from alpha to beta, right? So should we see any beta in the beginning? I mean, that's what our product is supposed to be, right? So no. So how should we write GI then? Do we write it as 1/4 GA? Write it as 1/4 GB? What do we write it as? Well, not 0, because then we wouldn't have any A, right? One. There we go. And specifically, one of what? GA or GB? GA, excellent, right? And that's because you're starting off with A. If you start off with A and your product is B, we're trying to get from A to B. You should have 100% A at the beginning, and that's what they said in the beginning of the problem, right? It said, as stated above, if 100% of alpha D-glucose turns into beta D-glucose, right? You start off with 100% 4 out of 4 GA, 4 out of 4 alpha glucose, and then your product could be entirely beta, it could be a mix of beta and alpha, right? It could be none of beta, right? Maybe it didn't go to, maybe the reaction didn't even complete at all, right? But those are our final and our initial states. The reason why I prefer to write it this way is that you can essentially plug this in here and plug that in there, right? And what you can see is that you'll have like 1/4 GB plus 3/4 GA, right? Minus GA, right? And so you might be thinking, well, how do I, like, what does that even do for me, right? If you further simplify it, you have 1/4 GB, and then 3/4 GA minus 4/4 GA, right, or 1 GA. 3/4 minus 1 would be what? Negative 1/4, right? So then you'd have minus 1/4 GA, right? What do you see here? Could we even simplify it a little bit more? Because remember, yeah, go ahead. How so? Yeah, how so? How could we separate it? Excellent. So we pull out the 1/4, and then we have GB minus GA, right? That way, 1/4 GB minus 1/4 GA, right? And so now we have our GB minus GA, which they already gave us a value for. That was negative 1.43. So effectively, you can write this as 1/4 times negative 1.43, and then that's how you can get your delta G for that first question, where 1/4 of the glucose ends up as beta D, right? And so it would just be a matter of doing the same kind of thought process, but for this one now. Does that make sense? Does that kind of clear it up? Awesome. Yeah, I mean, maybe another way to kind of do it quicker too. I just figured I'd show you like step by step like what's exactly going on here, because we want a final state, a mix of alpha and beta, an initial state of only alpha, right? I want to make sure that you're kind of understanding what's going on from like a reaction like system process from start to finish. But you can kind of expedite this by just looking at, well, if they said 1/4 of the glucose ends up as beta D, right? Then you can really just take 1/4 times that delta G. And if they ask what if 3/4 becomes beta D, then you just take 3/4 times that, for example, right? That's another way to expedite it there. But yeah, I will kind of erase this stuff real quick. But yeah, just to keep it simple and yeah. Anyway, but that one is kind of a weird problem, a little bit tricky to kind of think through and understand. But yeah, is that making a little bit more sense? Yeah. I want to say also, like, let me kind of look at something in the reading here real quick. I don't know if there's like a direct like statement anywhere in the reading that kind of says this, but you can kind of think of Gibbs free energy, right? What I want to say. Let me first look if there's a statement for it here. Okay. Yeah, I don't know if there's a specific statement for it. Well, let me think about this real quick. So products. So I'm wondering, like, you also think about how delta G, there's an equation for it in the reading that factors in your equilibrium expression, right? It's like delta G is equal to negative RT ln KEQ. So in a sense, obviously KEQ is a measurement of the like equilibrium concentrations, right? It's your equilibrium constant, it's your equilibrium expression. And that kind of shows us basically the concentration of the reactants, or the concentration of the products over the concentration of the reactants, right? And that concentration of the products versus the concentration of the reactants is kind of what we're looking at here, where you have 1/4 of the glucose as beta in your product, and 3/4 being alpha, as opposed to 100% alpha as your reactant, right? And so delta G can be considered as a measurement of, like, or I guess related to how complete a reaction is, right? Just from a conceptual kind of standpoint. You can kind of think about it as being related to how complete a reaction is, right? So really, if the goal here is trying to get everything converted from alpha to beta. So if you're only 1/4 of the way there, 1/4 of the beta, right? And you want to get to 4/4 of the beta, or 100% beta, right? That's the goal of any of these reactions, is to convert the reactants into products. if we're going by that conceptual kind of understanding that your Gibbs free energy is going to be related to the completion of a reaction, then if it's only 25% complete, or you have 1/4 of the beta as a result, right? Then 25% of your delta G value is what you should be getting, right? For that first question, for example. Does that kind of make sense? Like, I'm trying to think about it from a more conceptual like standpoint. If you didn't know how to like look at the equation from like GF and GI and all of that. I said the standard free energy delta G is equal to negative RT, like ideal gas constant RT, and then ln KEQ. Where KEQ is your so let me actually write the equation down here so you can see. Yep, yeah, I can go ahead and write it. Yeah, just don't write the negative sign for KEQ. So just negative RT ln KEQ. But yeah, that would be the kind of equation that I'm looking at. And then based on the fact that our equilibrium expression is products over reactants, right? Then if you only have 1/4 of your products produced, then you're 1/4 of the way of the reaction being completed, essentially. And so then you can kind of think about that as like, well, if 25% of the reaction is complete, then 25% of the G is like your value, essentially, at that point. Does that kind of make sense? Okay. Yeah, I mean, like I said, I'm gonna get more into like the reading stuff, and I'll make a PowerPoint as usual. It's just that I haven't gotten a chance quite yet to like go over like the exact theory of everything, but from just like a strictly formula kind of mathematical, perspective, that would be kind of the way to go about this problem, I believe. But yeah, I thought I should give you both kind of a conceptual standpoint and the mathematical perspective as to how to look at that stuff. But I think that's what's going on. I mean, I tried to do it in my head, kind of like where I said, okay, like if it's products over reactants, if we have 1/4 A, or 1/4 B, I mean, and you have 3/4 A, and we started off with just A, right? Then you get like 1/4 B over A, and 3/4, which is kind of weird. But yeah, then I got into that stuff, and I was like, all right, let me just like think about this without like necessarily the math, like keep the math and the concept separate, because then I was confused. I was like, all right, where do I go from here? But yeah, actually I know I don't know, I wouldn't say exactly where to go from here, because I guess if this is the natural log of like that expression, and if we separated things out, but nah, that doesn't work. Screw it. Yeah. Anyway, yeah, like I said, I'll like get into more of the conceptual like stuff later once I fully like finish kind of making a PowerPoint for all this stuff, but that's how to kind of go about it anyway. Let's see here, let me resume that screen recording there, and then after that, for 2C2, it's basically just plugging in different values for like, what is it? That if only a fraction x of the beta D glucose ends in solution, what should be the change? Delta G alpha to beta, right? So they're basically asking you to look at different percentages of beta D glucose produced, right? So we looked at 25%, we looked at 75%, so 1/4 and 3/4. So you can look for other values as well. Maybe 0, maybe 0.2, whatever you want, right? And plot those values. So basically just use different fractions, right, of beta glucose produced. Figure out the delta G for each of those fractions. All right, so if you did like 1/8 or whatever, I wouldn't recommend doing like those weird values. I just like, maybe I'd do like 0 or something as well. But yeah, figure out the delta G for each of those fractions, right? And then plot those values. So your x-axis is your different fractions, and your delta G is your y-axis, right? So x-axis is fractions, y-axis is delta G. And that's pretty much it for C2. C3 is kind of logical. It's just saying, like, when would you reach the smallest value, right? And if you think about it, right, if we're multiplying fractions by, like when I said you could kind of expedite it and just multiply the fraction by delta G, well, any fraction of delta G would have a smaller value, would have a bigger value. Let me say smaller or bigger magnitude. Let's look at that. So like if I had 3 joules, right? If I took half of that, do I get a smaller or a bigger value? Yeah, half of 3 joules, do I get a bigger or smaller value? Yeah, exactly, right? So any fraction of something, I'm going to get a smaller magnitude, right? In the case of delta G, now, since it's negative, right, I'll get a smaller magnitude, right? But do I get an increasing or a decreasing delta G value? So if I started off at negative 1.43 and I multiply it by some fraction, right? Based on our logic, we'll get a smaller magnitude. But technically, do we get a decreasing or an increasing delta G value? The more, like, we multiply it by a certain fraction. Exactly. Yep. You'd have an increasing delta G value. So if you started off 100%, right, is converted from alpha to beta, you'd have negative 1.43, right? You take a fraction of that, let's say 3/4, you'll get an ever decreasing magnitude, but an actual increasing value because you're going from negative and you're approaching 0, right? So that's the idea there. So really, any fraction you multiply it by will give you a larger value of delta G in terms of like being negative. Like negative 2 is greater than negative 3, but 2 is a smaller number than 3, for example, right? Like negative 3 smaller than negative 2, but 2, just the magnitude, is smaller than 3. And so really, when should you see your smallest value? Smallest value, not smallest magnitude, smallest value. Yeah, pretty much, and you just plot those values. But yeah, does anyone have an answer for like what, or have an idea of when you would reach the smallest value? I mean, you should get an idea too of like once you plot out the values, right? Yep, essentially. Yep, exactly, when x equals 1, right? Because like I said, if you have that number, right, negative 1.43, you multiply it by any fraction, right? If you multiply by 3/4 and then you multiply by 1/4 and whatever, right? Then you see a smaller magnitude. You might go from 1.43 to 1.20, right? But negative 1.43 to negative 1.20, what did you do? Did you increase or decrease your delta G value? From negative 1.43 to negative 1.2. Increased it. Exactly, getting closer to 0, so you increased it. And so effectively your smallest ever value would essentially be at 100%, right? So I'll just write, follow the plot you get. Now, let's see here. Is there anything else I want to add for this? I don't think so. Okay, so if we look at 2D1 now, right, then it's giving us a value or equation for delta S mix. They're saying smith something in analysis. As more beta D glucose is converted, different type of entropy change becomes crucial. Entropy of mixing. So they gave us the delta S mix equation, right? X is the fraction of beta D glucose and Y is the fraction of alpha D glucose. And then N, they said make that equal to Na. So if you see NaKB, what should you write it as? Because they said N is equal to Na in this case. Exactly, right? So effectively you can just write things as negative R XLN X, negative or minus R Y ln Y, right? That'd be the easiest way then to rewrite it there. Now, they said determine an improved expression for the total Gibbs free energy change, delta G total, by adding the effect of this entropy change to the simple delta G alpha to beta you found before. Okay, so let's see here. What do we want to do? It says, hence, recall that the entropy contributes to G by the term negative TS. Okay. And they told us that the temperature here is 25 degrees Celsius, right? Well, what they want us to figure out is delta G total, right? They want us to figure out what delta G total is, and they want us to add the effect of that entropy change to the simple delta G alpha to beta expression that we had, right? So, how should we write this? How should we kind of go about figuring this out? Think about what they're saying. They want you to figure out a total Gibbs free energy change right? And they're telling you the way you can figure out that Gibbs free energy. It says total Gibbs free energy, or determine that expression for the total Gibbs free energy by adding the entropy change at 25 degrees Celsius to the simple delta G you found before. So what are they telling you? They're telling you delta G total can be equated to adding entropy change to the delta G you found before. So, how should we set up an equation for this? Yeah, so that's what it is, from delta G alpha to beta, right? That's just the value that we had from before, which was that negative 1.43, right? So they're telling us that the delta G total, like this really requires kind of slowing down and reading the problem again. So it says the expression for the total Gibbs free energy change can be determined by adding, so that tells us that this can be determined, right? It's equal to, by adding your entropy change from before, the delta G alpha, right, to beta that we got from before, which was that negative 1.43, and adding it to this change in entropy, right? That change in entropy S mix. But here's the thing. It says the entropy contributes to G by the term minus TS, right? And so if you think about it too, delta G is in terms of what? What are the units for delta G? Yeah, so I see kilojoules per mole. Yeah, go ahead, Matthew. So we don't have delta H, right? Remember, we didn't get any indication of what delta H is, but you're on the right track, because what's that last part of the equation you said? Exactly. If entropy is in, well, actually, so we said that delta G is in the form of kilojoules per mole, right? And let's say we're talking about values of moles, right? Or just 1 mole, for example. Then really, and remember, this is energy, right? It gives free energy. So this should be in general, like values of joules or kilojoules, right? So if we're adding kilojoules to entropy, entropy isn't in kilojoules, right? What value is it? What are the units for entropy? What are the units for entropy, guys? Yeah, so excellent. Yeah, so it's J, so it's your joules per Kelvin, right? And also mole as well, right? And that's what we had, if you remember from a previous problem. Excellent. So we have on one end kilojoules per mole, and let's say even if we said it was kilojoules per mole here, right? We have this Kelvin. How can we get rid of that? Exactly, right? So 298K, by the way. Yep, no worries. But, and that's where the hint comes in too, because they said the entropy contributes to G by not just T delta S, but by minus T delta S, right? So this should be minus T delta S mix. So this is your value that we had from before, that negative 1.43, right? We have our temperature in the equation, in the problem, I mean, And our delta S mix, well, we can figure that out. I kind of already hinted at what that would be if you simplified it, right? So just that use that delta S mix equation that they gave you, and you can simplify it with the ideal gas constant that we were talking about before, because N equals Na in this case. So NaKb can become R. So you got R x ln x minus R y ln y, right? And basically, they're just asking you to figure out an expression. They're not telling you to calculate anything yet. So if you can just calculate an expression for that, right, as simplified as you can, then you're solid. So that's 2D1. All right, and then simplify. Don't calculate anything yet. 2D2, sort of what we were doing from before, right? And 2C2, I think, right? So basically, using that equation, plug in your different fractions for x, plug in your different fractions for y, and obviously x and y have to add up to each other, right? You can't, both sides of the equation have to add up to each other, right? And so, like if you have fraction of x of beta D-glucose as 0.1, then you have 0.9 as your alpha D-glucose, right? They have to add up to 1. Because like we were saying before, like we did 1/4 beta and we had 3/4 alpha, for example, right? You plug in those x and y fractions using that equations for delta S mix as well. And then using the equation for 2D1, right? That's how you can get your delta G total, and that's how you can fill it in the table there, right? And then effectively you just plot out all those values, 0.1, 0.2, 0.3, all those different mixture of fractions there, right? And that's how you can go about solving 2D2 there. So use equation from D1 and plot, basically, right? And then they're telling you how can you spot from the graph the fraction x of beta D-glucose at which the system reaches equilibrium, right? So if we're kind of looking at things from before, well, we determined, right, that the Gibbs free energy, whenever it's at a minimum, that's when we're at equilibrium, right? And so in this case, you would essentially just be looking at where your Gibbs free energy is at a minimum, and that would be when the system is reaching equilibrium, right? We determined that from before. So Gibbs at min, that's your equilibrium, right? So that is effectively kind of the steps that you need to take. And for that D part 2, you just go ahead and calculate every single fraction that you see, right? And just kind of write them out, your delta G totals and stuff. So that's not too bad. And then you just have to plot out all those combination of fractions and values. But that, I believe, is the gist of what's going on for the homework so far. Like I said, I will make sure to finish up like content review and stuff, and make sure to have PowerPoint for that uploaded, so you guys can use that for review, and hopefully I'll try to like figure out some more of the concept and stuff to make sure you guys understand the background of what's going on. But with that, I will end the recording. And I'll leave it open for any additional questions, and I have something to say here real quick before I end it as well. But yeah, that's the end of the recording. Thank you for watching.